So, hello and welcome to today's webinar with the topic How to Find and Avoid Vulnerabilities in Embedded Compilers. This is a joint webinar of Vector Informatik and Solid Sense. I would like to introduce our speakers. Our guest presenter is Marcel Beemster. He's CTO of Solid Sense. The other presenter today is my colleague Jason Masters. He's Field Applications Engineer at Vector. And last but not least, my name is Winfried Schröder. I'm Business Development Manager at Vector Informatik and responsible for the moderation of this webinar today. This is our short agenda for today. At first, let me give you a brief overview of Vector and our solutions. After this, Marcel will give you his lecture about how to find and avoid vulnerabilities in embedded compilers. In the demo session, Jason will show us how VectorCast handles different compilers and configurations. At the end of this webinar, we will answer your questions. Please ask your questions at any time by using the Q&A panel. So, as said, I'd like to start with a few words about Vector. Here are some facts and pictures about Vector Informatik. Our headquarters is placed in Stuttgart, and as you can see, we have 24 branches in 12 countries. Vector Informatik has about 2,500 employees and more than 7,500 customers worldwide. Vector offers automatic software testing solutions for all phases of testing, from the low-level software test to the complete system test. All tests can be performed locally on a PC or on a target platform. With the VectorCast product family, Vector Informatik is specialized on testing of embedded software written in C, C++, and Ada. 20 years ago, VectorCast was designed for the test of safety-critical software in the avionics, but today VectorCast is used in all industries, so the functional safety has to be proven. Looking at the V model, we find the VectorCast solutions on the bottom and on the right side in the rears of system and unit tests. On the left table, you see that VectorCast can be integrated with many of the tools you may already have in use for your software development. As you can see, VectorCast supports almost every embedded compiler available in the market. VectorCast supports 100% of the compiler code so that you can test your source code in the same way as it runs on the target platform. The VectorCast product family has to be qualified and certified by TÜV for use in safety-critical software projects. We offer certification kits to prove that your application has been well tested. It is always good to have an idea which test process is currently performed in a business and how this process should look in the future. This varies greatly from company to company. VectorCast can help you to reduce the time needed for software testing, to increase the test frequency, to increase the responsibilities for software testing within your organization, and to increase the amount of automated software testing. VectorCast helps you to push all these controls to the right side. So that's it from my side about Vector Informatik and our solutions. I now pass the microphone and the desk to Marcel and a speech about how to find and avoid vulnerabilities in embedded compilers. I will assign you the desk, Marcel.
Thank you, Winfried. Can you hear me?
Yes, very well.
Great. And now can you see my screen?
Yes.
Let's start at the starting slide. Here we go. All right. Yeah, we're going to take a look at compilers. In particular, we're going to look at errors in the compiler. It says vulnerabilities here, but yeah, really we're talking about bugs in the compiler. And they can be very nasty because as a software developer, you would like to be able to trust your compiler. You would like to do it to do the right thing. Now we're going to look at what if the compiler does not exactly do that thing that you expect. So we are based in Amsterdam. We are Solid Sense. We founded in 2014. We do services and we have a product for C and C++ compiler and library testing and validation. That product is called Supertest. It can be licensed. This product is a lot older than Solid Sense. So we started in 2014, but as we'll see later, Supertest started already in 1984, so that's more than 30 years ago. Fundamentally, Supertest is not very complicated. Basically, it is a very large collection of handwritten tests, and you see the T-test and the X-test. X-test, those stand for positive tests and negative tests. So we also do diagnostic testing. In addition, we have a large battery, a gigantic collection of generated tests. So the tests over here are handwritten, handcrafted to match exactly with the specification. But some parts of the specification, they lend themselves more to generation of testing code, and for that we have test there as well. In addition, we have some tools, a test driver and a test reporter. But the real complexity of Supertest, the knowledge of Supertest, is in those tests themselves, both the handwritten tests and the generated tests. Supertest also provides requirement traceability. So in the V model, we are not quite at the lowest level. We are not unit testing against the specific implementation. Supertest is built to match the language specification, the C and the C++ language specification. And Supertest provides evidence that the compiler has correctly implemented the language specification. That's our basic goal. With some more insight, you can also use Supertest at a more lower level. If you want to instrument the compiler, you can use it for unit testing as well. But basically, Supertest is independent of the compiler it is validating. So a short overview of what I'm going to tell you. First of all, a little bit about C, C++, why they're still relevant today and will stay relevant for a long time. And then, of course, a number of examples of compiler errors, because that's what you came here for. And then, well, what if you have a bug in this compiler? What can you do with it? How can you deal with such errors in the compiler? And then we have two topics, specific topics about testing that we're currently developing. One is for optimization testing, and the other is running Supertest on bare metal targets, where you don't have the luxury of operating system or runtime support. So let's start a little bit with the relevance of C and C++. So this graph is from a company Tioba in the Netherlands. There are more graphs like this, and they try to measure the popularity of the C and C, or actually a number of programming languages. They started this tracking in 2002, and now we're all the way up to 2019. And here the black bar, that is the bar for C. So I don't know exactly what causes this dip, but as you can see, C has been popular for a long time, and there's no reason to expect it will be less popular. C++ is also in the air. It's at the top 4 at the moment. C++ used to be a bit more popular. I think, yeah, I think with the upcoming area of all kinds of specific tools for web management, C++ became a little less popular here. Together, C and C++ still outdo the #1 Java in this flow. But of course, you cannot use Java for these very small, tiny embedded processors. So what makes C and C++ special in the programming language domain? So Their special qualities are first that C and C++ are portable to many different architectures. That gives rise to implementation-defined features, but you can run C on a 16-bit processor, a 24-bit processor, and there's not so many languages and compilers that can be so easily retargeted to those kind of processors as C and C++. C and C++ don't require much of an operating system or runtime system, so they can run on what we call bare metal systems with direct access to the hardware. They have little or no runtime system, and that means that there's no hidden overhead when you run your application. What you see is what you get, and also real-time aspects are important. And yeah, there's no runtime system that certainly takes away the execution of your program, the CPU, because it's the program that's running. Furthermore, the little overhead means that C and C++ can run with quite high performance, and that's also caused by the fact that compilers are so well developed. Compilers are existing for C and C++ also for more than 30-40 years. The GCC compiler has that age, and over the time it has been improved and further optimized to make the generated code faster. So also important advantages are this long history of C and C++. The languages are standardized by ISO, so they're the good language definitions, and those language definitions are also understood by the people that work with both the compilers, create the compilers, and the application developers. There's a huge ecosystem, and that means that both tools and developers are abundantly available. So for these reasons, C and C++ will stay relevant for quite some time. A little bit of history, I've already mentioned a bit about that. C started in 1972 famously as the underlying language for building the Unix operating system. K&R-C, the book, was published in 1978, and around 1989, the language was formally specified and defined by the ANSI and the ISO committees. Several updates of C have been made. C11 is the latest, but much of the industry is still working with C99, because that's an excellent basis for programming as well. Solid Sand we started, there we go again. Solid Sand we started around 2014 here, but Supertest here started right before actually the first standardized version of the ISO standard was made available. C++ started a bit later. It was sort of made public around 1985, and then followed the standards around 2000, and now the standards are speeding up, so we have 2011, 14 and 17 we have standards for C++ with quite some significant changes to the language. So a bit about the internal structure of the compiler. The compiler is really this long chain of stages. At the start we have, of course, we have our C source code that goes into the front end. The front end itself is a significant piece of work. That's quite a big part of the compiler. And then after the front end, the code goes into the analysis, transformations, and optimization phases until it gets to the code generator here, where the program is turned into assembly. If you run your compiler without optimization flags, then basically you skip much of the compiler and you go directly from the front end to the code generator, and you skip things like loop unrolling, get code removal, and other optimizations. Now this pinball machine here in the middle and this red line, that's a jagged red line, that indicates the sort of the random path that a program takes through the compiler and the instability of the path under modification. So if you make a small change to your source code, that may lead to a small difference here in the front end, but that small difference may expand itself so that by the time you get here in the optimizations, the path of the program is completely different, and you see completely different behavior of the internal optimizations of the phases in the compiler, and finally the assembly code may look completely different. Now these properties, they make, I summarize them here. So basically these properties make a compiler fairly easy to test because we have a very well defined input. So that's the language definition, and we know what we expect the compiler to do with that language definition. We have a single input, we have a single output, and the path to the compiler is deterministic. It is maybe unstable, but if you present the compiler with the same source code, you expect the path to be equal and the same assembly code to be generated. Now these properties make compiler very well suited for black box testing. The specification is very well known. Every test goes through every part of the compiler if you turn on the optimizations. And so every test basically verifies all these parts of the compiler. So that pipeline makes a compiler well testable. On the other hand, for developers, compilers are not so easy to do. They are unstable in the sense that a small change to the input or even a small change here in the third engine of the compiler makes the downstream of this path, this red path, go completely different, and the program may behave differently. So what that means, if you have written here a unit test for this phase over here, this optimization over here, and you've written that in source code, if another developer modifies something in an upstream engine, then you may not be able to see the same results for that unit test. So it may behave completely different. That makes it hard to write white box testing for compilers. The compiler itself is huge in size, so it can easily be many millions of lines of code. That also holds for the development team. On the GNU documentation, there's a list of about 500 developers that have contributed to the GCC compiler, and it says this list is probably not complete. I wouldn't be surprised if more than 1,000 people have worked on the GNU compiler over a time span of as I said, 40 years, and that's a very long time for a project, and those people were not all available at the same time. So that's a huge management issue for such a compiler. Compilers are never finished. One reason is that these new language standards come out. Another is that we have these non-functional requirements. We expect the compiler to optimize and optimize more. So as a result, compilers have errors. And now we're going to take a look at some of them. And I want to differentiate between errors because not all errors are equally bad. So first of all, the most lighthearted category is that of compile time errors. They may be not so nice because your program suddenly doesn't compile, your correct program doesn't compile, but at least it just doesn't generate incorrect code. Then there are the diagnostic errors. Those are errors that in the compiler, and they fail to diagnose errors in your source code, and they may even generate source code for something that's strictly speaking undefined in your in the language definition. We'll see an example of that as well. But then the real hard errors are the runtime errors. And again, we have two classifications of that: the mitigatable runtime errors, where there's a workaround possible, and the really bad runtime errors, where you really think, okay, if my compiler has this error, I may not be able to continue using it. So first of all, here's a compiler error, not a very bad compiler error, but it doesn't look nice, because if you feed this program into LLVM 3.9, I believe on a Linux system, then the compiler simply crashes. So the code has some incorrect programs, so the use of this x over here, which is the parameter of this function here, is not quite right. The compiler doesn't handle that well, and it crashes with a core dump and lots of diagnostic information about the compiler, which you cannot use to fix the program. But so that's a not so nice compiler error, but at least it doesn't incorrectly compile your program. So that's not really that bad. Then here we have a diagnostic failure. This is present in GCC, all versions of GCC and all versions of LLVM, because here we have a question mark colon statement where there's no expression between the question mark and the colon. So that's not according to the C specification. This is really an error according to the C specification. However, GCC a long time ago, the people that decided, okay, it would be a nice shortcut if we do allow this, and if you write this, what it means that if this is a positive value, not zero value, then the result of the expression is actually the value of this expression. So in GCC it has a meaning, but not according to the language specification. There's a way to turn on pedantic in GCC, but even that doesn't make it into an error. It just makes it into a warning of the compiler. So that's a diagnostic failure of the GCC compiler. Next, runtime error. This is a little bit more elaborate. I hope I have time to explain. But here we have two structure definitions, one with a phone number and a fax number. Here we have a definition of a house which contains that other structure with the phone number and the fax number. And I'm going to initialize this structure here, the context structure. Sorry, I have context structure and a house structure. I initialize a context structure with this notation over here. It's not so well known, but it's added in C99, this field-specific notation. It's actually quite friendly because it makes it clear which field you're initializing. And here in the generic structure, I'm initializing the phone number and the fax number. And then here in the home, I'm going to initialize the context structure first with the generic numbers, and then I override the phone number specifically with number 650. Well, if you do this in GCC, when it sees this phone number initialization, it completely forgets about the generic initialization over here. So instead of printing at this point a fax number of 999, it will print the value 0. Or yes, it will print the value 0, because if the field is not specified in such an initialization, it is initialized with 0. So this is a runtime error in GCC. Now, this is also quite a specific error. So this is what we call a mitigatable error. It's not so hard to verify your application to see that such an error is not in there, because it's not so hard to recognize this kind of initialization, maybe even automatically. But it can get a lot worse. This is from an embedded compiler, quite well used for quite a number of embedded processors. And here we see that we initialize an array element with the value 42. And here we have an alias assignment to the same array element. So we have an alias of this array in the as pointer, and we assign now -1 to the same location here as 0. And then if we check this, the value of the location, the compiler will tell you that this statement is true. So what has actually happened in this compiler is that it saw, okay, I've initialized as 0 by 42. It has forwarded this value into this expression here, and decided that the expression is true. So the alias analysis of this compiler is not correct. This is really bad, because if you cannot trust the alias analysis of the compiler, you should basically turn off optimization in the compiler. Now the next worst thing is that in this compiler, there was actually no optimization specified. This compiler always applies this optimization. You cannot even turn it off. There's no optimization to turn it off. And yeah, it's clearly very hard to mitigate, because it's not linked to a specific syntactical feature. And yeah, if you just say to the programmer, well, you can't use any aliasing, that's a hard task to meet. Here's another really bad optimization error. Let me shortly explain this C++ program. We have two classes here, class A, and it has one field X. Here we have class B. It inherits class A over here, and it also has a field called Y. So this class B has two fields, X and Y. And now on this side, we see that we create an object of class B. We initialize the Y field with number 2. That's happening over here. The initial value here is assigned to Y in this assignment. And then number 2 that was used here is passed to A to initialize the X value with number 2 minus 1 is 1. So we expect the X and the Y values, and that's tested here, to have the values 1 and 2. Now I'll show you what happens in the compiler. And this is not just a compiler, this is GCC. And here we have our test program on the left side. That's the same program I just showed you. And now here I've set up the generated code on the right side, and we're compiling with GCC for C++. The latest version, but it doesn't matter which version, because basically all the versions over the last 20 years, they have the same error. Now we're compiling with option -01, so we're optimizing, but not very aggressively. And we see here that the two fields of our object B, of type B, are initialized by 1 and 2. And that's correct. And well, the compiler has been clever. Here we see the test against numbers 1 and 2 that was over here. The compiler has been clever and merged that into a single value, which, if you look at the hexadecimal version, is actually the values 1 and 2 in an 8-bit long word. And so it tests against 1 and 2 at the same instruction. So that's very clever. But if we tell the compiler to optimize for size, and I've done that here, then suddenly it forgets about the initialization of one of the fields, and it only initializes the X field in the A class. And so this is simply very wrong. And so there's something wrong with, again, dev use analysis in this compiler. And yeah, it's not a good sign for being able to use inheritance in this compiler. I've got it also for the ARM compiler. This is for an x86 processor. Here's the same compiler for the ARM64 processor, and it actually does exactly the same. We have values 1 and 2 initialized when optimized with 01. When I change that to OS, then suddenly the initialization of 2 is disappearing, and we have a broken program. So those are two examples of really bad compiler errors. GCC in general is not so bad, I must say that. Here we have a typical scorecard of GCC when we're running supertests with it. And what we see here that, well, there are 103 compile time errors, so that sounds like a lot, but actually most of these are in the diagnostic area, and they're quite well avoidable and mitigatable. Those 4 runtime errors that we find here, they're also quite specific and they're avoidable. Now, what if you find a bug in a compiler? What do you do with? Well, of course, if you want it fixed, you have to report it to the compiler developers. Don't expect a quick fix, because compilers are very complex. And even if the fix can be made quickly, the verification that the fix works correctly, that takes time, and the distribution of the compiler also takes time. What you might expect from the developer is some kind of workaround. He or she may be able to define, okay, this is caused by specifically that condition. If you avoid that condition, then you will have no problem with this error. Is there a difference if you report to someone where you bought the compiler or open source compiler? Yeah, there is, but basically the difference is that with open source developers, it's really unpredictable what will happen. I've been working, when I was working on my PhD, on a GCC compiler with an optimization error in loops. It was Sunday morning, it was 10:30, I reported the bug, and half an hour later I got a patch for the compiler, and that fixed my compiler. So that was a very quick turnaround and fix of my test on Sunday morning, 10:30. That's not always going to happen. I've also reported a rather tricky bug in 2008. I don't even know if that was a Sunday, but the bug was not fixed. That was in GCC as well. It wasn't fixed until 2015, so that took 7 years to fix. It was quite a significant error as well, but it was hard to understand because it dealt with memory consistency system, and that was only really defined in C11. With a vendor, you can expect more predictable feedback. So there, within a week, you could expect at least some kind of feedback. Yes, we've seen the error. Yes, here's a workaround, and we're going to fix it in this amount of time. If there's a really big problem in your compiler, and you have the luxury of being able to select a different compiler, that may be what you have to do. It's not always possible. For certain embedded processors, there are not that many compilers around. If you're working in some kind of qualification process and you're working with a compiler that needs to be qualified for functional safety, then you don't have the luxury to switch the compiler typically, because this qualification process takes a long time and a lot of paperwork, and you can't just turn that around. So then a mitigation is what you need, and a workaround for that problem will help your developers get around it. Such a mitigation, of course, it would be nice if that would be an automatically checkable mitigation, so that the developer doesn't run into it accidentally. If the bug, if it's related to forgotten diagnostics, incorrect diagnostics, then you may get help from static analysis tools, and those static analysis tools will make sure that your code really adheres to the C language more than, for example, the GCC compiler does. And the earlier you start with a qualification of the compiler in a functional safety process, the more options you have. So our current research in improvements in compiler testing is trying to deal with optimizations. How do we verify this middle part of the compiler, this optimization part? Optimization is a non-functional requirement, so it's not about making sure that the program, the implementation behaves according to the specification, but it's about the speed of the program. Now, in some safety critical areas, people, and that happens in particular in aviation, it's quite common to say, well, we don't want the compiler to optimize at all because we don't trust this middle part. And if we use our -0, we can skip all of that and we can go directly into the code generator and use that. But we think there's good reasons not to do that. There can be a real cost to not using the optimizations. So here's a small experiment. We have this loop over here. It just adds a value, the iteration value, to a total, and it returns that. So this is a loop running n times. If we feed it with f99, so we call the function f with 999, and we do that 1 million times, we don't optimize. This loop runs in 2.7 seconds. If we optimize a little bit with 01, then it runs already 8 times faster. That's not so typical, but it is caused by the fact that this program doesn't use any memory. And if you further optimize to maximal optimization, then you get a program that runs about 15 times faster than the original. So that's quite significant. And well, if you want to see that in more graphic detail, suppose that you have your application running in the onboard computer of the car, and you can run that application when you compile with -01 and you need a computer of this size, it doesn't leave you many options, right? So if you want to take a sport, for example, you can do ping pong because that's all what fits into your trunk of the car. Now, if you compile with the maximum optimization level here, then you see that there's a little bit more space in the boot of your car, and you can even have a bit smaller car as well, because you don't need that big of a computing power here, and that gives you the options to choose, for example, golf for your sport. So that means really in practice that optimizations can have a huge economic value. If you compare no optimizations at all, which is sometimes used, to maximum optimizations, then it means 15 times less space for the compute hardware, and at the same time 50 times less heat dissipation, 15 times less cost for the hardware, and 15 times less power supply, smaller battery if you're working in a mobile device. So those are very significant costs if you put that all together of not using the optimization. So you may not have that luxury, and that's why we're looking into optimization correctness verification as well. And the question is how to do that. Well, it's often done with benchmarking. We know quite a lot of test suites that actually contain benchmarks, but they're not actually a good idea for verification of optimization correctness, and that is because benchmarks don't always verify results. They can have undefined behavior, so they may not actually behave according to the language standard, be defined according to the language standard. If there overflow in it, for example, it can still appear to work right, but not actually be right. It may not work with different data models, so in your 16 processor you're out of luck, and you may not execute and test all of the generated code. And that last point is what we're looking into in our research now. If we don't compile with optimization, and we have our same loop here again, we compile it and verify that all of the code, the assembly code, is generated by our test run, our unit test, then we see pluses all over, and that means all of the generated code is tested. If we compile with -02 here, run the same test, F99, we see that we get only 80% coverage. All the black stuff is covered, but the colored code is not covered at all by our unit test. Here we have a piece of code. It could be completely wrong because this test doesn't validate that red code is executed. Now 80% sounds like quite close to 100 already, but if we look at the branch statements here, we see that we have here a branch statement that is fully covered. It has a plus, but most of the branch statement, these are not covered at all. This one is tested only in one direction. This one is tested one direction, one direction, one direction. So quite a lot of our branch statements are not tested in two directions at all. Most of all, if we try to gain maximum coverage for this code, we need at least 5 tests for the code, 5 different unit tests, and that finally gives us maximum coverage for the code. So we're building this new optimization suite. We aim at maximum branch and code coverage. We're testing that with 3 different compiler families so that we have reasonable expectation that it also works for other compilers. We make sure that we have verifiable results. We can support different data models, and we make sure we have no undefined behavior. Here's an example of the ICC. That's the Intel compiler with our new optimization test. And this is a mean test, I must say, but it results in a runtime segmentation fault for the Intel compiler, which is quite well known for its high level of optimization and high performance of the generated code. So not so nice. We really have a segmentation fault of the generated code when we compile with -02. Another thing we're looking at, so stepping away from optimizations, is making support for freestanding environments better. So if you have your application for a very small processor that just controls maybe the windscreen wiper on your car. You don't need a very big processor for that. You want to run in a very small processor. But is that processor large enough to run a test suite on? Now we're trying to make sure that our test suite can run within 4K of instruction memory and 2K of data memory. So we're really trying to make Supertest work well for these very small processors as well. And we can run on without support from an operating system or runtime system, and make sure that we have a minimal driver interface. So in short, to round off, no compiler is perfect. And in mission critical applications, safety critical applications, you need to know what are the weak points of your compiler. Supertest is a very good tool to do that. It's useful for both compiler developers and compiler users. If you are a compiler user and you don't want to run the test suite yourself, at least verify with your compiler supplier what kind of test suites they are using. If they're not using Supertest, well, maybe push them to do that, because we really know that every compiler that we got our hands on that has not been tested with Supertest, we find rather big holes and runtime errors that are not so nice and that you don't want to run into. So we really believe Supertest is the best test suite for C, C++ compilers. And we, of course, offer the test suite, but also expertise and services in this domain. So to round off, to hand over back to the guys from Vector, they're going to demonstrate integration of Supertest with VectorCast. And thank you for your attention. You can ask questions, of course. Please put them in the Q&A bar, and I'll hand back to Winfried now. Thank you, Winfried.
Yes, thank you, Marcel, for this great lecture. As I said, I will now hand over to Jason Masters and his presentation.
Okay, thank you very much. Good afternoon, everyone. Okay, I'm just going to show a very quick presentation about VectorCast and what we're going to look at. So VectorCast QA is a tool that we can use to automate the process of system testing. If we think about what we need to do if we want to run some tests and get some code coverage of our compiler, we have to take our compiler source code, instrument it, build a executable, and then compile some code to exercise the compiler, and then from there we get some coverage data. And VectorCast QA sits in here and enables us to automate the stages of testing, which means that we can make the testing repeatable and make it quick. So we have some test cases here, and these are our Supertest test cases, and we can put them into a list of tests that we can either hard code or generate dynamically. And we have a Python script that controls the instrumenting and building of the source code, and then it will decide what tests to run based on the results it has already. If there's no test results, it will run all of the tests. And then if a particular test or source code changes, we'll see what happens with that in the next slide. But we can run the tests, get the coverage data, and load that into VectorCast QA. And then we can also view the code coverage. So when we run our compiler, we can see that that pinball trace Marcel was talking about. We can see exactly what lines of code were covered in our compiler as we compiled a piece of code. If we think about what happens if we change our source code, and in the development process we might be making some optimizations to one part of our source code, and obviously we want to verify that that change hasn't broken anything. But the question to ask is, which tests do I need to rerun to verify a particular code change? Now, because of the way the code pass through the compiler happen, we might not know which tests go through a particular function that we're changing. And so to manually work that out probably takes as much time as it does to rerun all of the tests. So VectorCast can operate in a change-based testing mode. So we can store the code coverage for each test. And if you come in and modify a function, so for example here we have version 1 of our source code and version 2, and we've made some changes to the function bar, VectorCast can store the coverage from each test and know which functions it went through. So if we change this function here, we can look at our tests in our test database and see which tests we need to rerun. So from the entire list of tests, we can work out the tests that went through the bar function and then just rerun those tests again. So this means that if we make some changes to our compiler, we can quickly check and make sure that our changes have worked, but also perhaps more importantly, we haven't broken anything else. That's one of the main problems with changing source code. It can be quite easy to verify that your change has had your desired effect, but much harder to verify that it hasn't had some other effect as well. And so doing change-based testing means that we can effectively rerun our tests again, and VectorCast will decide which tests need to be rerun to verify the changed lines of code. We can then take that a bit further and then take this and put it into something like Jenkins or Bamboo, Team Foundation Server, or some other continuous integration system, so that we can commit our code, our changes, and have our continuous integration server get a trigger from our version control system, check out our updated code, and do an incremental build and execute on our VectorCast QA project, and have Jenkins do the hard work for us and run the tests. So this means that we can make changes to our compiler, commit them, and then be sure that the appropriate tests are being run. So this makes streamlining of the tests much easier, and it gives us a continual reassurance that the changes we're making we aren't storing up lots of major problems when it comes to release. So that's a very quick overview. Let's have a look at what we've got in practice. So I've got a compiler here. I've got my compiler files here. I'm actually using something called the Tinyc Compiler, which is a very small compiler. Obviously, in the real world, compilers like LLVM and GCC and commercial compilers are composed of many more files. But I've chosen this one because it's nice and simple and doesn't take very long to build, and it's easy for me to navigate my way around the compiler. And so I put that into a VectorCast project, and I'm just going to go in, and we can see we have some test results from our previous runs. What I'm going to do is I'm just going to remove those so we can go back to having no results. And so in VectorCast QA, we have a Python script which handles all of the automation. So this means that we can customize our VectorCast project to cope with many different build systems and run many different cover projects. So there's a few simple configuration items here that tell us where our project is, how we build our project, where our tests are, where the command we're going to use to run our tests. And here we're using the supertest command to run our test. And in here I've hard-coded my tests because I don't want to run all of the tests in supertest. As Marcel mentioned, there's a huge amount of tests within supertest. I don't want to run all of them because that will take ages in terms of a demo. So I've just hard-coded a few, but we could write a function that goes and gets the tests, or perhaps we could get our tests from our requirement system, or whatever. It doesn't really matter. It's all configured via Python. And then I've just got some other functions that tell me how to run my test, and also a bit of code that analyzes the output from supertest, so we can get more feedback on what happened when we ran some tests. So let's just clear all of that and then do a build execute. So when we do that, the Python script comes in and looks to see if any of the source files have changed since the last time we ran it. If they have, it will instrument any files that have changed. It then call the build program. In this case, it's just a simple batch file. Obviously, in a real world, we'd probably have some more kind of sophisticated makefile or build system that would do an incremental build. And then we start running the tests, and we can see we're running the super test tests here. And so for each test, we're compiling the source file using our Tinyc Compiler and gathering the coverage, and also gathering the results of the test, so we can see if the test passed or failed. So we can see we have an incremental rebuild report here that tells us what happened. We can see there's 6 tests that we ran because the results were missing because I just previously deleted them. And we can see the test names there. If I go and do a build execute again, Vectorcast will go through the same process and it will see what's happened. Has the source code changed? No. Have the tests changed? Are there any new tests? Have I deleted any tests? No. So it will just come back very quickly and report that nothing really needs doing. So as we've run those tests, we've got 2 things from running those tests. We have some code coverage. And so this is code coverage of the compiler, not the code coverage of the compiled tests. So this shows us the paths through the compiler. So the coverage for each test is stored individually, and as we select the test, we can see exactly what code was covered. So if I just select all of the tests, we can see what how much code was covered in each test. And we can go and have a look in more detail in each file. We can see the green lines are lines that are covered and have been executed. If we scroll down a little further, we can find we have some branches where we've only gone down either the true or the false branch of each condition. So obviously there's some more tests to be run here to make sure we've executed both the true and the false for each of these branches. And again, we can see that for every one of the files in the project. So that tells us our coverage, and the code coverage is useful for testing completeness. If we've covered all of the code paths, we know that we've tested all of our code. If after running the test we still have some code that hasn't been covered, we can ask ourselves the question, what is that code for? What is the purpose of that code that hasn't been executed? Is it perhaps defensive code, which is okay to leave in there? Or is it code that in fact has no purpose and could be removed? So as well as the code coverage, we also have the test results. So here we can see that only 3 out of our 6 tests passed. So we've got a 50% pass rate. So I've added a little extension onto Vectorcast that allows us to have a look at the results of the test execution. So we can see we've got 3 tests that have failed here. The second and the third one have failed in the compilation phase, and the other one has failed in the runtime as well. And we can double click here and have a look at what the issue is. And so here in the source code, there's a unsigned long double, and the compiler has has incorrectly compiled this code without giving a diagnostic, and so this leads to the question of exactly what type is this? This is an illegal type, but the compiler generated some code. What type is this? Is it a long? Is it a double? We don't know. So that's obviously a danger there. And then in the this one here, this test here, we've got a conversion between a double and a long double, and it failed it passed the compilation but produced incorrect output. So there's a bug in our compiler. And so we can go and fix that bug and then rerun our tests and verify that we've fixed the bug and also that we haven't introduced any more bugs. So the question is where is the bug? And so somewhere the bug will be somewhere in the lines of code we've covered. Exactly where it is kind of a slight art in terms of finding bugs. You need to know your way around the code, but just looking at some code here, I can see there's a potential bug here. There's a comment here that says get first element, and someone's using 1 to index an array to get the first element. Perhaps there used to be an ADA programmer where arrays started at 1, but in C we know that arrays start at 0. So I think that's probably a mistake there. So let's go and have a look at the source code, and we can change that. Vectorcast. Let's just change it. It's just a regular text editor. So we've now changed that. So now we've changed our code. Let's go back and do a build execute and see what happens. So there's a little exclamation mark saying something has changed, and we're rebuilding. We can see in here that we've instrumented the file that we've changed. Because we changed it, we have to re-instrument it. And now we're building that new executable, a new compiler, and then we're going to run the tests. But we're only going to run the tests that need running. There's no point running tests that don't go through that function we changed because they won't be affected. So we can see here that we've just changed one, just needed to run one test again. You can see the summary up here. 5 tests were preserved and 1 was run. And then we can also hover over here and see that we've now got 4 passing tests. So our pass rate's gone up to 66%. So we can obviously think if we have hundreds of tests here, we can obviously get much quicker verification that we haven't broken anything by using the change-based testing. So obviously here I'm just working on the host, and we talked about embedded compilers and things like that. And Vectorcast supports a huge number of compilers. So at the moment I'm using MinGW. So I'm using MinGW to compile my compiler, and then that's obviously running on the host. But we can run the compiled executable on target as well, in the same way that supertest can run on a target as well. We can support running on target. So even if we were doing system testing outside of using supertest, we'd still be able to run code on the target and get coverage results back from running any application on a target on pretty much any embedded platform. And so we can see we support a huge number of different compilers and different combinations of compilers and platforms and targets. So that is a very brief overview of Vectorcast. I mean, I've been working in the GUI here, but everything I've done in the GUI can be redone on the command line. So it's open to automation, and we have a Jenkins plugin as well that can quite easily run this and do the same thing from Jenkins as well. Okay, so I think that's the end of the demo. I'd like to hand back to Winfried to moderate the question and answer session.
Yes, thank you, Jason, for this demo of Vectorcast. It's now time for the Q&A session. So please feel free to send us the questions you probably have. Please use the Q&A window and send us your questions to all panelists. Marcel, do you got any questions you can answer so far?
Yes, I do. Can I have the screen again?
Yes. the screen.
All right. You should see me now.
Yes.
Okay, my question window is disappearing, but the question was, are the issues that you've shown reported to, in particular, the GCC compiler? Well, some of them are very new. So the last one I showed with the assembly code and the 1 and the 2, that's a very new one. So I'm pretty sure that's not reported. This runtime error, this with the initialization of the fields here, that's been in our demo for years and years already. So this is a very old problem in GCC. It's been reported as far as I know, but yeah, that's what you sometimes have with open source compiler developers. You may not get the attention that you want for fixing a bug. So this bug has been there for ages, and it will probably stay there for ages. It's not. Yeah, if nobody picks it up and nobody's bothered by it, and it will not be fixed. I showed you an Intel compiler error. Yeah, this is one we have reported to Intel, but of course we didn't just give it to Intel. We also asked them, well, it's now high time that you're going to use supertest as well. So we use that usually as an encouragement to take a look at our tools as well. Next question. Now I need my window. I have to stop sharing for a moment. Next question. Who defines the test cases used by supertest to qualify the compiler? Who defines the test cases used by supertest to qualify? Is there any statement on test coverage? So, well, basically what we do for, let me share the screen again. Winfried, can I have the screen again?
Oh, sorry.
Yeah,
I just moved back to my screen.
Yeah, sorry.
Hold on a second. What's that? So you have it back.
Yes. So basically, our test cases are defined by the language specification. So for every paragraph, basically, that there is in the language specification, we aim to have a test, and if needed, we have more than one test, and that provides us with the traceability from the tests back to the language specification, and also with the traceability from the language specification back to supertest. And yeah, we have, of course, different language specifications. It's C, C99, C11, C90, and for C++ even more. So there's a little bit of administration required there as well, but we can show how the tests map to the language specification. And if you want to qualify for C99 specifically, then you define the subset in supertest for the C99 language, and that will give you the coverage that you need for qualification. So I have to read the question and answers again, and then right. If a company assures that the compiler is qualified for ISO AD in ISO 26262 systems, does this mean that there is a 100% test coverage? Okay, then I have to go a little bit into the, I'm going to share again. I'm going to go a little bit into the requirements of the qualification. I've got a couple of slides here, basically. Yeah, if you need to qualify the compiler, and you need to do that if you have an application that is at ISO level D, then you have to use one of these qualification methods. And the qualification method that is typically used for compilers is qualification by testing. Other alternatives are take a look at the process under which the compiler was developed, the development process, for example. But given a compiler that's been developed for 40 years, that's not really an option. But testing is something you can do as a black box, and so the testing that Supertest provides is black box testing. So tool qualification in ISO 26262 does not require MCDC coverage of the tool sources itself. It requires that the tool behaves according to its specification and that you validate that it behaves according to the specification. And that's what we do with Supertest. We provide the tests according to the specification, and that allows you to validate the compiler. So if a compiler is guaranteed or actually has as an HLD qualification, it doesn't mean that the compiler sources have been MCDC validated at 100%. It also doesn't imply that the compiler is free of errors. The qualification process is basically a process that is, as I said, it's a process. You have to take the compiler through it. Out of that process comes documentation on what is possible with the compiler. So if the validation process finds errors in the compiler, you have to define in the documentation, the qualification documentation, these are the errors that we have found. This is the use case that we have qualified for. So if the qualification is for no optimizations, that qualification is not valid for running the same compiler with optimizations or with a different optimization level. So having qualified a compiler doesn't mean it's bug-free. It may have mitigating actions that you are required to do if you use that compiler, and you have to strictly adhere to the use case for which the qualification has been done. So what you get with a qualification certificate like that is also quite restrictive. It is for a specific version of the compiler. It is limiting to you to a use case, and if those restrictions are too much, then you may have to do your qualification yourself. But that's indeed possible with something like Supertest. So I'll read the next question.
I think there's a question for me here.
Yeah, Jason.
Is Vectorcast using only the test library from Supertest or any other Supertest tool capabilities? So for this demo, I'm using the test suite from Supertest, so all of the test files, and I'm also using the usual way of running a test using Supertest. So although Supertest on its own can run all of the test files, in Vectorcast I configure it to run just one test at a time, so I can get the code coverage for each test individually. So I'm just using for the demo just a subset of the Supertest test files and the normal program that comes with Supertest to run each test file. So I wasn't using any of the generated tests. So I was just using a kind of subset of the features available from Supertest. That's not to say I couldn't use all of the other features, but just for the demo to keep it simple and easy, I've just chosen a subset of features to use. But the Vectorcast itself, when it comes to using QA, because there's a Python script that you can use to customize and interact with your product, it can be configured to work with a wide range of software, whether it's a compiler or an embedded device or anything.
There's another question. Winfrey, do we still have time to answer a question?
Yes. I see there's a question for Jason.
Yes, I've just answered that one about Vectorcast. Yeah.
Okay. Then I would say we will come to the end of this webinar now, but we will let the Q&A window open for additional questions before I close the webinar completely. I would like to thank you, Marcel and Jason, for your presentations. I like to thank all attendees for your interest and the time you spent with us. I hope you enjoyed the webinar and we can welcome you again in one of our next webinars. I wish you all a great day and a successful rest of the week. Goodbye.